This is the story of a number that quietly governs every landing at the highest commercial airport in America. It is not the runway length. It is not the weather. It is a thermodynamic limit written into the flight manual of every jet that touches down at Telluride Regional Airport. And it explains why a Gulfstream that lands easily at sea level can find itself in trouble at 9,070 feet. Telluride sits on a mesa in the San Juan Mountains of Colorado, surrounded on three sides by peaks rising to 14,000 feet. The single runway, 927, is 7,111 feet long, and both ends drop into a 1,000-foot cliff that falls away into the San Miguel River Valley. There is no overrun. There is no second chance, and on a warm summer day, when the density altitude climbs past 11,000 feet, even modest jets start running into a problem that almost no passenger has ever heard of. The brakes cannot absorb the energy. At 9,070 feet above sea level, Telluride Regional Airport is not simply high, it's perched on a mesa, hemmed in by mountains and defined by its geometry as much as its altitude. The runway, 7,111 feet from threshold to threshold, sits atop a narrow plateau with a 1,000-foot drop at each end. There are no grassy overruns, no gentle slopes to cushion a miscalculation. The boundaries are absolute, asphalt, then cliff. At both ends, a concrete EMAS bed, engineered to crush and absorb the energy of an overrun, offers the only margin between a stopped aircraft and open air. But the EMAS is just 400 feet long, barely a safety net at this scale. Standing at the edge, the runway feels finite in a way that few pilots ever experience. Every landing here is a calculation against the void. There is no room to float the touchdown or to gamble with speed. If an aircraft crosses the threshold too fast or too heavy, there are only seconds to recover. No second approach, no chance to go around once the wheels are down and the brakes are engaged. The terrain itself enforces discipline. The cliffs are not just a backdrop, they dictate the consequences of every decision made in the cockpit. The airport manager describes the environment with a quiet certainty. Here, you get one shot. The margin for error is measured in feet, not hundreds. Every pilot knows you either stop on the runway or you don't stop at all. This is the real constraint at Telluride, not the weather, not the length on paper, but the hard limits imposed by elevation, geography, and the physics of stopping. Before any talk of brake energy or thermodynamics, the mesa itself makes clear. There is no forgiveness for misjudged speed or distance. The runway is a test of precision, and the cliffs are always waiting at the end. On the approach into Telluride, the cockpit instruments tell only half the story. Indicated airspeed, what the pilot sees on the dial, remains fixed, a familiar number used for every landing checklist. But at 9,000 feet, the atmosphere is thin, and the physics quietly rewrite the rules. For every 1,000 feet of elevation, true airspeed climbs by roughly 2%, even though the indicated airspeed stays the same. By the time a Gulfstream G450 lines up on final at Telluride, a standard approach of 130 knots indicated has become 156 knots over the ground. The wings do not notice. The brakes do. That hidden increase in speed carries a steep penalty. Kinetic energy at touchdown is not a linear function of speed. It grows with the square. A 20% rise in true airspeed means a 44% surge in the energy the brakes must absorb. What feels like a routine landing at sea level becomes a test of thermodynamics on the mesa. The numbers are unforgiving. What would be 1.2 million foot-pounds of energy at sea level swells to nearly 1.7 million at Telluride's summer density altitudes. Cockpit telemetry from the G450 confirms this reality. Data logs show approach speeds cresting 155 knots on warm days, with landing distances stretching well beyond what the performance tables predict at lower fields. The energy spike is invisible from the cabin, but pilots know the margin is gone. Here, geography becomes a physics problem, and every foot of runway is measured against the relentless math of velocity squared. The result is a landing environment where advanced carbon brakes are not a luxury. They are a necessity. Before heat, before wear, before even the first touch of tire to asphalt, the thin air has already stacked the odds. The mountain is not the enemy. The true challenge lies in the energy that must be tamed before the cliffs at the far end come into play. In the maintenance hangar, a chief technician holds a carbon brake disc, a dense matte black ring layered with the scars of high-energy landings. This is not ordinary hardware. Carbon-carbon composite, woven and baked at over 2,000 degrees Celsius, is engineered for extremes that would destroy steel. On a typical Telluride arrival, about 40% of the jet's kinetic energy is dumped into these discs. For a Gulfstream G450 at landing weight, that means nearly 600,000 foot-pounds of energy, enough to push the disc surface to 500 to 600 degrees Celsius in seconds. The rest of the energy is shed by spoilers and reverse thrust, but the brakes alone must absorb the surge and survive. The technician runs a finger along the disc's edge, explaining that carbon's secret is its ability to soak up heat rapidly without warping or losing friction. Where steel would fade or even melt above 800 degrees Celsius, carbon remains stable up to 1400, sometimes even 1800 degrees Celsius in a short maximum energy stop. The material's high thermal conductivity spreads heat across the stack, while its emissivity allows it to radiate energy away once the aircraft is parked. But the margin is not infinite. Each disc is certified for a cumulative energy ceiling of 115 million foot-pounds before mandatory removal and inspection. Every landing at Telluride carves a measurable chunk from that total. The technician's logbook tracks each event, each spike in temperature, each approach that pushes the disc closer to its limit. In this environment, the brakes are not just a component. They are the gatekeeper between a successful stop and the abyss beyond the runway. The Gulfstream G450's braking system is defined by two numbers, 115 million foot-pounds and 91 million foot-pounds. These are not recommendations, they are boundaries, set in certification documents, and they are enforced by both physics and policy. Every landing at Telluride carves into that margin. The cumulative energy absorbed by each brake stack is tracked with the precision of a countdown clock. Once a disc reaches 91 million foot-pounds, it must be removed and undergo a detailed inspection before it can return to service. Cross the 115 million mark, and the disc is retired, no matter its appearance. But the system's ultimate backstop is not a number on a chart. It is the fuse plug, a small sacrificial device embedded in each wheel hub, designed to melt at 1,350 degrees Celsius. If brake temperatures spike past this threshold, the plug liquefies, venting the tire before the heat can trigger an explosive failure. 3 fuse plugs per main wheel stand between a controlled stop and a catastrophic blowout. When one melts, the aircraft is grounded until the entire brake assembly is replaced. The downtime is measured in hours, the cost in tens of thousands of dollars, but the alternative is unacceptable. The maintenance chief's logbooks are filled with stories of landings that push too close to the edge. A single fuse plug activation halts the operation, triggers a mandatory teardown, and demands a fresh brake stack flown in from a distant hub. There is no negotiation with these limits. The brake system's energy ceiling and its sacrificial plugs draw a hard line between what is possible and what is permitted. At Telluride, that line is not theoretical. It is the difference between a safe turnaround and a stranded jet perched on the edge of a mesa. The clock starts the moment the wheels stop turning. At Telluride, the discipline begins on the ramp, where every minute of brake cooling is tracked with the same attention as fuel or weather. The airport manager, standing by the operations board, enforces a strict minimum. No jet departs until the brake temperature has dropped below the threshold set by the Gulfstream BKE chart. For a G450 arriving at maximum landing weight in summer, that means a cooling interval of at least 1 hour, often longer. The thin mountain air strips away convective cooling, cutting the coefficient to less than 1/3 of its sea level value. What would be a 20-minute wait in Denver becomes a 60-minute standstill on the mesa. Weight management is non-negotiable. The BKE chart, dog-eared and annotated, becomes the Bible for every arrival. Inputs such as landing weight, ambient temperature, and runway condition are double-checked against the chart's energy limits. If the numbers threaten to breach the 91 million foot-pound inspection line, the crew offloads fuel or delays the approach. There is no margin for improvisation. The procedures are explicit. No second landing, no taxi back, until the brake stack is cool enough to guarantee another stop without crossing into the red. The airport manager's authority is absolute. Pilots, mechanics, and dispatchers all answer to the numbers. The runway may be open, but the brakes decide when the jet can move again. EMAS is the last line of defense at Telluride. The engineered material arresting system, 400 feet of crushable concrete at each end, exists for one purpose: to halt an aircraft that overruns the runway when every other safeguard has failed. The airport manager stands by the threshold, eyes on the pale gray bed, and explains that the EMAS is rated for a single, high-energy stop. It will decelerate a Gulfstream G450 from 70 knots to 0 within its length, but only once, and only if the aircraft enters straight and under control. There is no buffer beyond. At Aspen, the runway is longer by 900 feet, and the terrain slopes away rather than dropping off a cliff. El Alto, at 13,300 feet, faces even thinner air and a 55% kinetic energy penalty, but its 11,000-foot runway and broad safety zones absorb the risk. Telluride's EMAS is a hard stop, not a cushion. It is engineered to save lives, not airplanes. Every number, runway length, field elevation, arrestor capacity, converges on a single truth. Here, the margin is measured not in comfort, but in survival. At 9,070 feet, the wings ignore the altitude. Only the brakes record the truth. A 44% surge in kinetic energy cannot be negotiated or deferred. It must be mastered or it overwhelms. Here, the landscape does not dictate danger. The laws of thermodynamics do. Physics, not scenery, draws the line.